At 10:44 on the morning of December 5th, 2024, the seafloor west of Cape Mendocino broke with the force of a magnitude 7.0 earthquake. Phones sounded across California and Oregon. A tsunami warning flashed along the coast while residents moved inland and waited for the ocean to answer. The feared wave never arrived, but the rupture had struck one of the most complicated pieces of crust anywhere in North America. 11 days later, scientists lowered ocean-bottom seismometers into the cold Pacific, racing to record aftershocks before their patterns faded. Those instruments captured hundreds of events. But another investigation, already listening inland, found the clue, now changing the map. It was a faint, repeating shiver far below Northern California, too small to feel and too slow to resemble an ordinary earthquake. These signals were gathering between roughly 22 and 29 kilometers deep, in a place where the standard tectonic diagram looked almost empty. They returned in recognizable families, sometimes on intervals of only about 2 days, as though one hidden surface kept slipping again and again. When researchers traced their geometry, the tremors formed a dipping line beneath the region where the San Andreas system meets Cascadia. That should have clarified the famous Mendocino Triple Junction. Instead, it revealed that the name itself may be misleading. The junction is usually drawn on a flat map as 3 plates meeting at 3 clean boundaries: Pacific, North American, and Gorda. But in January 2026, a study in Science presented evidence that at least 5 moving pieces are involved beneath the surface. One is a buried remnant of an ancient oceanic plate, captured long ago and now being dragged north with the Pacific plate. Another appears to be material torn from North America and carried downward beside the sinking Gorda slab at the junction's southern edge. Above the buried fragment lies a deep detachment surface that does not appear on ordinary maps and was absent from existing national hazard models. Its seismic potential remains unknown. It may creep quietly, or it may be capable of rare ruptures that instruments have never recorded. The discovery does not mean a giant earthquake is imminent. The tiny tremors are not a countdown toward catastrophe. But it means the machinery beneath Northern California is arranged differently from the geometry used to estimate where earthquakes can begin. It also offers a new explanation for a mystery left behind by the devastating 1992 Cape Mendocino earthquake near Petrolia. That magnitude 7.2 event ruptured much closer to the surface than the accepted position of the subducting slab seemed to allow. For more than 3 decades, the earthquake looked misplaced. The new model suggests the fault was misplaced on the map instead. The hidden plate fragment has a name: Pioneer. Its story began nearly 30 million years before the alarms of 2024 sounded. At that time, the western edge of North America faced the enormous Farallon Plate, an oceanic plate that was steadily being consumed beneath the continent. Along much of the margin, Farallon crust descended into the mantle, releasing fluids, feeding volcanic arcs, and building the tectonic architecture of the American West. Far offshore, however, the Farallon Plate was splitting apart along a spreading ridge. On opposite sides of that ridge, newly created oceanic crust moved in different directions. As the ridge approached the continent, the geometry of subduction became unstable. A trench cannot continue swallowing 2 plates that are moving away from the ridge between them in the same simple way. Around 30 million years ago, part of that spreading system reached the North American margin. The old subduction boundary began to give way to a new kind of contact. The Pacific Plate met North America directly, and the early San Andreas transform system began to form between them. That transition did not happen everywhere at once. 2 junctions migrated in opposite directions along the coast, as more of the spreading ridge encountered the continent. The southern junction moved toward what became the Gulf of California. The northern one advanced toward Cape Mendocino, lengthening the San Andreas system behind it. The moving northern junction rearranged slabs, faulted the lower crust, compressed wedges of sediment, and left fragments of oceanic lithosphere where a plate diagram says they should no longer exist. The Pioneer fragment is one survivor. Earlier, geophysical models proposed that a partially subducted piece of Farallon lithosphere became attached to the Pacific Plate during the boundary's birth. Instead of sinking with the rest of the Farallon Plate, it was captured and carried northwest. That idea remained difficult to test. A buried slab fragment cannot be photographed, drilled, or followed by a surface line. Scientists had to infer it from seismic velocities, crustal reflections, gravity, deformation, and the way earthquakes lined up at depth. Even then, competing models could explain the same evidence. One placed a slab window immediately south of the Gorda Plate, where the old slab had vanished and hot mantle could rise. Another proposed that the Pioneer fragment still occupied part of that space. No single method could resolve the question because velocity anomalies can reflect temperature, fluids, composition, or geometry, and each interpretation placed stress on different surfaces. Both possibilities mattered. A slab window changes heat flow, melting, uplift, and volcanism. A captured slab changes which plates touch, where they exchange stress, and how far a buried fault extends beneath the continent. The difference changes the inventory of earthquake sources. The decisive evidence came from signals few would recognize as earthquakes. Ordinary earthquakes begin abruptly when brittle rock fails, producing sharp arrivals across many frequencies. Low-frequency earthquakes are weaker, richer in lower-frequency energy, and commonly embedded in tectonic tremor. Tremor can sound in processed seismic data, less like a single crack and more like a distant engine. It often occurs near the deep transition between a locked fault and a region sliding more steadily. There, high temperature and pressure make rocks behave differently, while fluids can reduce the effective friction holding a fault closed. A low-frequency earthquake is not simply a small version of a damaging shock. Many repeat on the same tiny patch, producing nearly identical waveforms. That repetition allows researchers to build a template from a clear event, scan years of continuous records, and identify thousands of weaker matches hidden inside noise. The Mendocino signals form 27 recognizable families, their locations aligned along a zone dipping about 45 degrees toward the north-northeast, extending eastward and downward from a neighboring band of persistent micro-earthquakes. The families occupied depths of roughly 22 to 29 kilometers and recurred unusually often. Their position was already strange. They sat 50 to 100 kilometers west of the main belt of Cascadia tremor and near the southern edge of the Gorda slab. They could have marked normal faulting at the rim of a slab window, motion between the Pacific and Gorda plates, or oblique slip involving the buried Pioneer fragment. Location alone could not choose among those explanations. A line of hypocenters reveals a fault's orientation, but not which direction the sides move. The team combined two tests: first motions of seismic waves and the earthquake's response to tides. When an earthquake begins, the first P wave pushes some stations away from the source and pulls others toward it. That pattern constrains the mechanism. Because these signals were weak, researchers stacked many events and compared them with ordinary earthquakes. The resulting mechanism indicated dipping, right lateral strike-slip motion. In other words, the two sides were moving mostly past each other, not simply separating as expected for normal faulting at the edge of an empty slab window. The orientation closely matched the relative motion expected between the Pacific and Gorda plates. Then came the tidal test. The gravity of the moon and sun does not only raise the oceans, it flexes the solid earth and produces tiny changes in stress inside faults. Those changes are far too small to cause an earthquake on a strong fault that is not already close to slipping. But deep tremor zones can be exquisitely sensitive. If fluid pressure is high and effective friction is low, a small tidal stress can alter when a weak patch releases. The team calculated which fault orientations would be encouraged by the tides at the moments when the low-frequency earthquakes occurred. The event rate increased systematically when tidal shear stress promoted the same strike-slip direction inferred from the seismic first motions. Two independent clues pointed to the same kinematics. The tremors were tracking relative motion between the Pacific side and the Gorda side at depth. That result transformed the interpretation. Pacific-like motion was occurring southeast of the surface expression of the Triple Junction, beneath North American crust. The simplest explanation was that the Pioneer fragment had indeed been captured by the Pacific Plate and was translating northward underneath the continent. The fragment is not actively diving northward like the Gorda Plate. Its buried upper surface dips eastward, but the fragment is being carried mainly north with the Pacific Plate. At its northern boundary, it rubs past material associated with the Gorda slab, producing the repeating low-frequency earthquakes. The Mendocino transform may not stop where its offshore trace ends. At depth, the boundary can continue eastward beneath land as a concealed strike-slip interface. The surface map shows a junction. The deep structure resembles overlapping layers in a moving stack. The second hidden piece makes that stack stranger. Tomography identified a corridor of low P-wave velocity north of the low-frequency earthquakes. Slow velocity can indicate hotter, fractured, fluid-rich, or compositionally different rock. Earlier interpretations treated this zone as thickened North American crust. The new fault motion suggests something more dynamic. The low-velocity material may once have belonged to the North American accretionary prism, the wedge of water-rich sediment scraped from the descending oceanic plate and piled against the continent. Near the Triple Junction, the Pacific Plate presses northward while the Gorda Plate moves obliquely northeast beneath North America. The intervening crust experiences intense north-south compression. In the proposed model, part of the accretionary prism escaped that squeeze by being forced downward onto the Gorda slab. Material once added to the continent would therefore be subducting again. It rides above the denser petrologic slab, shifting the actual fault interface southward and upward from the boundary that researchers had inferred by tracking the Gorda Plate itself. That distinction is crucial. A petrologic slab is the physical body of oceanic lithosphere identified by its composition, velocity, and internal earthquakes. A plate boundary fault is the surface along which large-scale relative motion occurs. In simple models, the two are treated as nearly interchangeable. At southern Cascadia, they may be separated by about 10 kilometers. The primary interface could run across the top of a thick, subducted wedge, while the recognizable Gorda slab lies deeper. A hazard model built on the slab's upper surface could therefore place the active boundary too far below the ground. This is where the 1992 Cape Mendocino earthquake returns to the story. On April 25th, a magnitude 7.2 thrust earthquake struck near Petrolia. It produced intense shaking, landslides, fires, damaged buildings, and a small tsunami. 2 powerful offshore aftershocks followed the next day. The main shock occurred at a depth of about 10 kilometers, roughly 10 kilometers above the Gorda slab position used in later models. Because its thrust motion looked like subduction, early studies interpreted it as rupture of the plate interface. As slab images improved, the explanation became harder to reconcile with the depth. Some researchers instead placed the earthquake on a smaller fault inside the overriding plate. The new geometry revives the original intuition in a different form. The 1992 rupture may have occurred on the true subduction interface, but that interface was not sitting directly on the petrologic Gorda slab. A magnitude 6.0 honeydew earthquake in 1991 and continuing thrust microearthquakes also align with this shallower structure. Together, they suggest that southernmost Cascadia bends through former continental material before meeting the deeper slab. Not every earthquake near Cape Mendocino belongs to one fault. Strike-slip events rupture the Mendocino transform. Intraslab earthquakes break inside the Gorda Plate. Thrust events occur on or near the subduction interface, while crustal faults carry motion inland. That compact overlap is why earthquakes separated by only a few kilometers can have different depths, motions, aftershock patterns, and hazards. That complexity explains why nearby earthquakes can behave so differently. On December 20th, 2021, a compound sequence near Petrolia released its largest energy in 2 closely spaced shocks. Exactly 1 year later, the magnitude 6.4 Ferndale earthquake struck within the Gorda Plate at about 18 kilometers depth, damaging communities across the Eel River region. Then, the magnitude 7.0 event of December 2024 ruptured the Mendocino transform offshore. 3 strong sequences in a few years did not represent one fault repeatedly failing. They exposed 3-dimensional strain being partitioned across neighboring pieces that move in different directions. The same principle applies to the newly inferred detachment above the Pioneer fragment. The science study found no ordinary earthquake sequence directly outlining that surface. Its existence is inferred from the fragment's motion, deeper velocity structure, active seismic imaging, the way the San Andreas system must connect into the buried geometry. A detachment is a low-angle fault separating rocks moving differently above and below. In this case, it would lie between the northward-moving Pioneer fragment and the North American crust. The northern San Andreas system may merge into it at depth, while the Macama and possibly Bartlett Springs faults help distribute motion farther east. If the detachment slips steadily, it may transfer plate motion without producing great earthquakes. If much of it is locked, its size and the roughly 51 millimeters per year of Pacific North American relative motion make its potential more consequential. At present, neither possibility has been demonstrated. That uncertainty is why the phrase unaccounted hazard must be handled carefully. It does not mean scientists discovered a guaranteed magnitude 8 fault ready to break. It means a potentially large fault surface was absent from the source inventory used in national seismic calculations, and its behavior is not yet constrained. Hazard models depend on geometry. The depth, dip, length, segmentation, and slip rate of a fault affect expected earthquake magnitude, shaking intensity, and the probability that a rupture will reach another structure. Move an interface 10 kilometers closer to the surface, and the same amount of fault slip can produce stronger local shaking. Change the length over which 2 plate systems touch. And stress transfer scenarios also change. The buried Pioneer fragment may extend the zone of contact between the San Andreas transform system and the Cascadia subduction system farther inland and farther east than surface maps imply. That does not prove one great earthquake will trigger another. Dynamic stresses from large ruptures travel enormous distances, yet most faults do not immediately fail. Whether a neighboring system responds depends on its stress state, friction, geometry, fluids, and where the incoming waves concentrate. Still, the revised geometry removes some of the separation once assumed between the 2 systems. Instead of meeting at a neat coastal point, Cascadia and the Pacific North American boundary may overlap through a broad volume of faults and fragments. Interaction becomes physically more plausible, even if its probability remains unknown. The historical record cannot resolve that probability by itself. The full Cascadia margin last ruptured in January 1700, before modern instruments and written records in the Pacific Northwest. The event is reconstructed from coastal subsidence, drowned forests, indigenous histories, offshore deposits, and a tsunami recorded across the Pacific and Japan. The northern San Andreas produced its defining modern rupture in 1906, tearing hundreds of kilometers toward Cape Mendocino. Yet 1 or 2 great earthquakes do not reveal the full range of ways a complex junction can fail. Geological archives extend the record, but their timing and fault attribution carry uncertainty. This is why the low-frequency earthquakes matter so much. They provide a near-continuous tracer of motion on deep faults that otherwise reveal themselves only during rare destructive events. Instead of waiting centuries for the system to expose its architecture, researchers can listen to its smallest recurring slips. The signals are thousands of times too weak to be felt, but their repetition turns them into markers. If a family accelerates, pauses, migrates, or changes its tidal sensitivity after a nearby earthquake, it may reveal how stress and fluids moved through the buried boundary. That information is not a deterministic prediction tool. No pattern of tremor can currently specify the date, location, and magnitude of a future damaging earthquake. The value lies in improving the physical model, identifying which surfaces move, how they connect, and whether their slip rates change after major events. Monitoring above the junction is changing too. After the 2024 magnitude 7.0 earthquake, rapid response ocean bottom instruments were deployed within 11 days, while dense temporary land arrays recorded aftershocks that permanent stations would have located less precisely. In Arcata, distributed acoustic sensing turns buried telecommunications fiber into thousands of closely spaced strain sensors. The experiment captured regional earthquakes and showed that shaking can vary sharply over only a few hundred meters. The 2022 Ferndale earthquake demonstrated why that matters. Sediments in the Eel River Basin amplified higher frequency motion by more than a factor of 2. Deep geometry controls incoming waves, but shallow ground determines much of the damage. The migrating Triple Junction also altered heat and volcanism south of Cape Mendocino. As the Farallon slab fragmented, hotter mantle helped create the volcanic and geothermal landscape of the Coast Ranges, including Clear Lake and the geysers. Modern tomography also images a multi-level magmatic system beneath the geysers' Clear Lake area, evidence of long tectonic reorganization rather than an eruption warning. The Pioneer fragment complicates that classic slab window picture rather than erasing it. The opening may be irregular, partly occupied by fossil lithosphere and bordered by pieces moving in different directions. Northern California's faults, geothermal heat, and deformed crust are linked products of a plate boundary still assembling itself. On a human timescale, tectonic plates seem permanent. On a geological timescale, the Mendocino Triple Junction is a traveling construction zone. It moves north with a Pacific plate, continually converting a subduction margin into a transform boundary while dragging remnants of the old system beneath the new one. Even the Gorda Plate is not a rigid, passive slab. It is a small southern fragment of the Juan de Fuca system, squeezed between surrounding plates and internally deformed. Numerous earthquakes occur within it because the plate bends, twists, and breaks as it approaches and descends beneath North America. The Pioneer fragment adds another layer to that deformation. Its motion forces the Gorda side, the buried sediment wedge, and the North American crust to accommodate contact over a greater area. The repeating low-frequency earthquakes mark one of the places where that accommodation is happening now. Now must be understood correctly. The fragment was not suddenly discovered because it began moving in 2026. It has probably been traveling north for millions of years. What changed was scientific visibility. A signal that had blended into seismic noise became a tool for resolving direction, depth, and plate identity. Headlines can make better detection look like sudden awakening. Machine learning, template matching, and denser networks now find events older systems missed. More dots on a map may reflect sharper observation, and most swarms or aftershock sequences do not precede a larger earthquake. But better observation can reveal that an old probability was calculated with an incomplete model. The 2026 study changes the questions scientists must ask. How far east does the Pioneer detachment extend? Does it creep? Is it segmented? How strongly is it coupled to the crust above? Researchers also need to determine whether the low-frequency earthquake zone changes after large nearby ruptures. The 2024 magnitude 7.0 event occurred west of the junction on the Mendocino Transform. If deep slip rates shifted afterward, the repeating families may preserve that response more clearly than surface GPS. Another question concerns fluids. Accretionary prisms begin as water-rich marine sediment. As they are buried, heated, and compressed, fluids are expelled and pore pressure can rise. High pressure reduces the effective normal stress clamping faults together, allowing tremor and slow slip under conditions where dry rock would remain stable. The observed low-frequency earthquakes may therefore illuminate both motion and material. Their location beside the low-velocity corridor suggests a boundary where deformation, fluid release, and contrasting rock types interact. Persistent micro-earthquakes nearby may represent fluid-assisted fracturing above the deeper plate contact. Yet fluids do not remove tectonic forcing. The repeating events align with plate motion directions and respond to tidal shear on the inferred fault. Water may regulate when weak patches slip, but the long-term engine is the relentless relative motion of the Pacific, Gorda, and North American systems. That engine moves at rates measured in centimeters per year, about the pace at which fingernails grow. The movement feels trivial until it is multiplied across decades, centuries, and hundreds of kilometers of fault. Elastic strain accumulates silently, then releases in seconds. Cape Mendocino experiences that release more often than most of Cascadia. The broader Cascadia megathrust is comparatively quiet between major events, while the Triple Junction repeatedly produces magnitude 6 and 7 earthquakes on different structures. High activity does not necessarily mean the megathrust is closer to rupture, but it makes the southern boundary unusually informative. It may also make the boundary unusually influential. A future Cascadia rupture could begin far to the north near the Triple Junction or somewhere between. The new study suggests the southern end contains a shallow interface, an extended buried transform boundary, and a detachment of unknown behavior crowded into the same region. Rupture simulations will eventually have to test that geometry. A fault closer to the surface may alter coastal shaking and deformation. A broader overlap zone may affect whether rupture stops, turns, transfers stress, or continues onto an adjacent structure. Those models will not produce certainty. They will produce ranges of physically defensible outcomes, which can then guide building codes, tsunami planning, emergency exercises, and the placement of instruments. The purpose of mapping hidden faults is not to create fear. It is to replace a false simplicity with usable detail. For Humboldt and Mendocino communities, the practical hazards remain familiar. Strong shaking, landslides, damaged bridges and utilities, liquefaction in soft sediment, fires, and possible tsunami effects. The new model changes the source geometry, not the need for resilience. Early warning remains one defense. During the 2024 magnitude 7.0 earthquake, roughly 5 million alerts reached phones in California and Oregon, providing anywhere from a few seconds to tens of seconds before stronger shaking, depending on location. The system does not predict an earthquake. It detects rupture after it starts and outruns the strongest waves with electronic messages. Future coverage will combine denser seafloor arrays, fiber optic sensing, improved three-dimensional velocity models, GPS, tomography, and continuous catalogs of tremor. Each method sees a different part of the system, from strong ruptures to weak deep slip. When those observations are combined, the Mendocino Triple Junction no longer resembles three lines touching on a flat map. It becomes a layered mechanical system. The Pacific Plate and its captured Pioneer fragment moving north, the Gorda Slab descending northeast, North American material being drawn downward, and faults threading between them. Some of those faults rupture violently, some creep, some tremble in signals that require years of stacking to detect. Some may remain locked so completely that their existence is visible only through the motion around them. That is the central contradiction beneath Northern California. The smallest earthquakes have revealed the possibility of a much larger fault, while the largest historical earthquakes now make more sense because of motion too weak for anyone to feel. The 1992 rupture was not necessarily an anomaly floating above the plate boundary. The boundary itself may rise through a buried wedge. The anomalous tremor was not random noise south of Cascadia. It may be the audible edge of a fossil plate still traveling under the continent. And the Triple Junction is not a single point. It is a broad, evolving collision where at least 5 pieces exchange motion across surfaces that overlap in 3 dimensions. Back on December 5th, 2024, the magnitude 7.0 earthquake ended within minutes, the tsunami warning was canceled, and the coast returned to an uneasy normal. But the aftershocks and the quieter signals remained. They led scientists beneath the familiar faults, past the clean textbook boundaries, and into a structure assembled from captured oceanic crust and recycled continental sediment. Something is changing beneath Northern California, but the most important change is not a sudden awakening. It is our picture of what has been moving there all along. The ground did not become more complicated in 2026. We finally learned how complicated it already was.